you for introducing me, and thanks to the organizers for having me and giving me this opportunity to present this joint work with Georg Hofstätter and Oscar Ortega-Moreno. So first things first, I think I have to tell you what these words in the title here mean. So valuations, we have already seen some of them in the workshop, in the talks of Monika and Jonas and Dimal, real valued valuations, measure valued valuations, but I will talk about convex body valued valuations. So a Minkowski valuation is a map from the space of convex bodies in Euclidean space Rn into the space of convex bodies. It has this the valuation property, this inclusion-exclusion principle, but with the sum here, with the addition being the usual Minkowski addition. So this is a Minkowski valuation, and I will, and the setting will be, we will focus on continuous Minkowski valuations that are translation invariant, homogeneous, let's say homogeneous of degree I, and SON equivariant, meaning that they commute with all rotations and in particular preserve all the symmetries of a convex body. We have already seen such Minkowski valuations in the talks of Dylan and Ellie, like the difference body map and the projection body map, but maybe one of my favorite examples of such Minkowski valuations are the so-called mean section operators. So they were introduced by Goody and Weil, and they work as follows. So imagine some n-dimensional convex body, and then what we do is we take random j-dimensional sections of this convex body, and the way this works is we endow the space of the Grassmannian of j-dimensional affine subspaces of Rn with some rigid motion invariant measure. This plays the role of the probability measure, and then we take all these random j-dimensional sections, and then the expected value, the mean, is again a convex body, and this is then the jth mean section body of K. And we can define it in terms of this, with this formula by means of the support function. This operator here, the jth mean section operator, is a Minkowski valuation. It is homogeneous, commutes with all rotations. It is not translation invariant, but there's this can easily be fixed by subtracting the Steiner point. This is not an issue. And then we are in this space M bar I. So this is such an example where, of course, I and J have to match accordingly. So I hope this makes sense so far. So these are the Minkowski valuations I would like to talk about. Next, the Lefschetz operators. So we have the space of convex bodies, then we have the Minkowski valuations acting on the convex bodies, and then on top of that now we have these Lefschetz operators that are operating on these Minkowski valuations. So the L operator here, this integration operator, is in a similar construction as we have just seen. So we start with the Minkowski valuation phi, and now we map it to another Minkowski valuation as follows. So given a convex body K, we intersect K with all possible affine hyperplanes, plug these into the given Minkowski valuation, and then we take the average. And then this defines, again, the Minkowski valuations, all the nice properties, the invariances are preserved, and the degree of homogeneity is increased by 1. And what if we apply this to our example? Well, the jth mean section operator gets mapped to the j-1 mean section operator. Essentially just because a random j-dimensional section intersected with a random hyperplane gives a random j-1 dimensional section. Okay? This is one Lefschetz operator, and then we have another one. So we had an integration operator, and we also have here a derivation operator. It's not the inverse operator. I like to think of it more as a sibling, in a sense. And it works as follows. So given the Minkowski valuation phi, we define a new Minkowski valuation lambda phi as follows. So we given the convex body K, we plug in this outer parallel set, K plus T times the unit ball. We plug this into the Minkowski evaluation, and then we take the derivative with respect to T at 0. And in contrast to the Lefschetz integration operator, here it is not actually clear a priori that this is well defined, that you again get something convex body valued. However, due to a result of Parapatitz and Schuster, we know that this is in fact the case, and Minkowski evaluation gets mapped to Minkowski evaluation. And again, all the nice properties are preserved, and the degree of homogeneity is now decreased by 1 by this derivation operator. Okay. Now, why do we care about these Lefschetz operators? So, as you can see, these operators allow us to move between different spaces of valuations of different degrees of homogeneity. And in this sense, in this way, these operators have been used to transfer certain results of valuations of a given degree to valuations of another degree. Yeah? For instance, certain geometric inequalities, isoparametric type inequalities, or Brun-Minkowski type inequalities, and I believe we will see more of that tomorrow in Andreas' talk. And another reason to look at these Lefschetz operators is that we do not have a full understanding, a complete characterization of this space M val I. And so this is also a reason why I would like to understand how these Lefschetz operators act on the Minkowski evaluations and on these spaces. Okay, so what we do know about the space M val I is we have a kind of Hartwigger type theorem due to Schuster and Wannerer. And the theorem says the following, so given a Minkowski evaluation phi in this space, there exists an S or n minus 1 invariant integrable function f phi, continuous on the unit sphere minus the poles, such that we have an integral representation, namely the support function of the Minkowski evaluation applied to K can be written as the ith order area measure of K, spherical convolution with f phi. So this theorem needs a little bit of explanation. So this function f phi, that is kind of the protagonist in this theorem, is S or n minus 1 invariant. And by this, we mean that here we fix the north pole and the south pole of the unit sphere, and we have an axis of revolution. By S or n minus 1, I denote all the rotations that fix this axis of revolution, and the function f phi is now invariant under all these rotations. So in particular, the function f phi actually corresponds to a function on the interval minus 1, 1, here denoted by f phi bar. So actually all the information is contained in a real function, in a function living on a one-dimensional interval.
Question?
Mm-hmm.
The direction of the unit vector you choose is arbitrary.
So yeah, so the north pole, the choice of the north pole is kind of arbitrary here. So this function is S minus 1 invariant, integrable, and continuous up to the poles. The ith order area measure can be obtained from the surface area measure, for instance, by a Steiner formula, and this symbol here denotes the spherical convolution. I don't want to go too much into detail, but there is a natural way to define a convolution structure on the unit sphere. It has this convolution product has all the nice properties that you would expect, only that we always wanted the right factor to be something S or n minus 1 invariant. Okay. What I should also say is that in fact Schuster and Wannerer first proved this representation, but with f phi only being a signed measure. Then around the same time Dorek discovered that actually this is an integrable function, not just a measure. And then more recently Oscar Ortega-Moreno and myself further refined this by establishing the continuity. Yeah, this function f phi depends uniquely on the Minkowski evaluation up to some linear component that we don't care about, and we call it the generating function of phi. And this generating function turns out to be a very helpful, a very powerful tool when working with Minkowski evaluations. And in particular, what I have said before now, the questions that we have about Minkowski evaluations can be phrased, can be formulated in terms of this generating function.
Sorry. For every f by y, you get such evaluation.
No. So we do not know, in general, which functions are generating Minkowski evaluations. So for instance, whenever you have a convex body of evolution, then its support function is such a generating function. This works in every dimension and for every degree, but we do not have a full characterization.
Any conjecture about it?
Not really, no. I mean, also you have to keep in mind that this space of Minkowski evaluations is not a linear space; it's only a convex cone. So this also makes it more difficult to find a characterization. Okay. So now we can ask, how do the Lefschetz operators, we want to understand the action of the Minkowski evaluations. Now having this Hartwiger type theorem, we can ask how do they act on the generating function. So the derivation operator, recall this was plugging in k plus t times the unit ball and taking the derivative with respect to t. So if you're familiar with the area measures, with this or the area measures, you might know that there's a Steiner formula, and if we do this here, then the ith area measure just becomes the I minus 1 area measure. But the generating function stays the same, essentially. So the action of the lambda operator is actually very easy. The generating function is just preserved. So there's nothing much more to say. So we can set the lambda operator aside. And for the L operator, for the Lefschetz integration operator, it becomes more intricate. So due to Schuster and Vannevar, we know that the action is in terms of some convolution transform. So there exists some SON minus 1 invariant distribution rho I, such that the generating function of L phi is the generating function of phi, spherical convolution with this rho I. And this distribution rho only depends, of course, on the dimension and the degree, but not on the Minkowski evaluation, so it's some kind of universal, it's universal in a sense. However, this description doesn't provide any like geometric information. So for instance, Van Schuster posed the question, what if a Minkowski evaluation is generated by a body of evolution, and we apply the operator L, is this then again generated by a body of evolution? Purely from this, there's no way to say. This is now our main result. So we can show that this distribution rho I turns out to be an integrable function, actually, which is also smooth on the unit sphere minus the North Pole, and it is also strictly positive. This is our result. Well, and in particular, we can give a positive answer to this question. So the answer is yes. If a Minkowski evaluation is generated by some body of evolution, then Lefschetz operator L applied to this Minkowski evaluation is as well. Okay, and in the remaining time, since I believe that the proof is quite neat, I would like to show you, well, how we prove this. Okay, so first I need to make a little bit of preparation. So we have already observed how the Lefschetz operator, the Lefschetz integration operator, acts on these mean section operators. We just map one mean section operator to the other. And from this, we already know this. Okay, so we know this. Okay, so now what is the generating function of such a mean section operator? Well, this was done by Goody and Weil in 2014. So they computed these generating functions, and it turns out that the jth mean section operator is generated by the jth Berg functions. And these Berg functions, this is like a family of functions on the interval -1, 1, and that were introduced by Christian Berg in 1969. They are connected to the Christoffel problem, but the important thing for now is that we have quite a good understanding of these functions, and and they will play a crucial role now. And in fact, this particular relation that we have, so the action on the mean section operators, on this one particular family of Minkowski evaluations, will provide us all the information that we need in a sense. And here, in order to do so, we use just a little bit of harmonic, we need a little bit of harmonic analysis. So whenever we have an SOn-1 invariant distribution on the unit sphere, such as a generating function or this distribution rho I, then we can write it as a kind of Fourier series. So here P and K denotes the Legendre polynomial corresponding to dimension n and of degree k, and this number A and K of gamma is essentially the Fourier coefficient. So if gamma would be an L2 function, this would be just a classical Fourier series, right? Because these Legendre polynomials they are orthogonal. But this also works for distribution, only that the convergence now is in the weak sense. Okay, and now the neat thing about these Fourier coefficients here is that a convolution product of two such distributions corresponds to just the product of these Fourier coefficients. We have an algebra homomorphism. Okay, but now we can use this identity here and combine this with this theorem by Goody and Weil. Just combine all the things that we know now, and then we get that this Fourier coefficient here is just a quotient of the Fourier coefficients of the Berg functions. Well, and fortunately, these have been computed explicitly by Bernig and Hug, and also independently by Berg, Partitz, Schuster, Webendorfer. So now we just can plug these numbers in, compute the quotient, and we get something that, well, some expression of gamma functions, which is not too bad, let's say. Okay, so in a sense, we already know the distribution rho I because we know the Fourier coefficients, so we can just look at the Fourier expansion. So now naively one could say, well, we want to prove that these rho I's are positive and smooth. We have this Fourier series. Well, so let's just look what the Fourier series converges to. If it converges to something positive and smooth, then we're done. However, if we do that, for instance here in dimension 4 and for degree 2, then we see that here the convergence is only in a very weak sense. We have high oscillation, and this doesn't converge. There's no pointwise convergence even. So no, we can show no regularity or positivity this way. Okay, so we have to be a little bit clever. And on the last slide, I would like to give you the idea how we solve this. So the first step is to realize all of these distributions as distributions on the interval -1, 1. Yeah? So these rows, they are SOn -1 invariant, and therefore they all correspond to some distribution on the interval -1, 1. And this is crucial because now all of these rows coming from different dimensions now live on the same space. Okay, and then the next step is that by looking at this, purely just by looking at the Fourier coefficients and exploiting the structure of the Fourier coefficients, we can establish certain relations. So the first one here, rho n I, is equal to rho n minus I minus 1. This is like trivial, this is immediate from looking at the Fourier coefficients. The next one here, this relation here, means that we can express some of these rows as the box operator. This is some second order differential operator of a Berg function. Okay, and then the third one here, this is a recurrence relation where we express one of these rows as a derivative of a different row. And note here that we relate two different rows to each other, corresponding not only to different degrees, but also to different dimensions. So this is why it's so crucial to work on the interval -1, 1. And these three relations combined provide a complete recursion that allow us to trace back all of these rows to the Berg functions. And recall that we have like a good understanding of the Berg functions. And in this way we can we get some control, we get some hold of all of these rows. Yeah. this is how we can establish the regularity. So we obtain that all of these rows, they are smooth. Also smooth around the South Pole. At t equals 1, as t goes to 1, we have a singularity. So this corresponds to the North Pole. We have a singularity, this goes to plus infinity, and also we know the precise order of the singularity, and so on. And then we can establish a second order differential equation for these rows. So we do this using the recurrence, and then by some induction argument, because we also have differential equations for the Berg functions, by an induction argument we can establish the second order differential equation, and also this is a way now to define or to characterize the rows, because, yeah. And then the only thing that remains now to show is the strict positivity. Right? We have established the smoothness, and the smoothness already immediately implies, of course, the integrability, because it's a distribution. So the only thing that remains to show now is the positivity. And how do we do this? Well, at the North Pole, we take on the value plus infinity. At the South Pole, we can also show, so at t equals -1, we can also show that the rows are positive. Well, and this differential equation here is a strictly elliptic second order differential equation. So by applying the strong maximum principle, we also get that they are strictly positive. Well, and that's all I wanted to say.